want to instantly level up your understanding of generative AI, you're definitely in the right place.
Absolutely.
Yeah, forget just recognizing images or text. This is about AI that can actually create stuff. Things that have never existed before. That's the fundamental shift we're diving into today.
Exactly. And we've pulled together quite a bit of material on this.
Right.
Our goal really is to just pull out the crucial insights for you. We want you to get a handle on how this breakthrough happened.
Okay.
What's going on under the hood, but without getting totally bogged down in the weeds.
Yeah, keep it manageable.
Right. And what it could do now, and the big important considerations we need to think about as it keeps evolving.
So 0 to informed, fast track.
That's the idea. Yeah.
So let's look at how we actually got here. Our sources point to, 3 key phases?
Yeah, broadly speaking.
First, the machine learning evolution, roughly 1980s to 2010.
That's the one, the groundwork.
Then the deep learning revolution, that was 2010 to 2016.
Yep. Things really started heating up then.
And finally, the generative breakthrough period, which started around 2017 and is still accelerating like crazy today.
It really is. It's been a rapid transformation.
So within those periods, were there specific moments that really stand out?
Oh, absolutely. Yeah. Think about 2010 to 2012.
Okay.
That's when deep neural networks started doing amazing things with image recognition.
Right, like identifying cats in photos, that kind of.
Exactly, but way better than before. It showed the power of these deeper, multi-layered networks, a really foundational step.
Okay, got it. Then 2014, GNs.
Yes, generative adversarial networks. Ian Goodfellow.
That felt like a totally new way of thinking about it, didn't it? This idea of two networks sort of fighting.
It's a fascinating concept, that competitive learning. You got one AI, the generator, trying to make fake stuff look real, and another AI, the discriminator, acting like a detective, trying to spot the fakes.
So they push each other.
Exactly. This back and forth forces both of them to improve really quickly. It's a genuinely new approach.
Okay, then 2015, you mentioned LSTMs, long short-term memory.
Yeah, and improved RNNs, recurrent neural networks. These were big steps for handling sequences better, especially text.
So making AI-written text sound less robotic?
Pretty much. You saw a real jump in coherence in how well the generated text flowed and made sense.
Right. And didn't we also start seeing creative visual stuff around then? Like style transfer?
We did. 2015, 2016, those early algorithms let you make, your holiday snaps look like a Van Gogh painting.
Oh, yeah, I remember those apps. They were everywhere for a bit.
It was an early hint of AI's, let's say, artistic potential, a glimpse of creative visual generation.
Fun times. Okay, 2016 sounds like another big one. WaveNet.
WaveNet, yeah.
Yeah.
That made computer-generated speech sound much more natural, much less choppy. A big leap for audio.
And something called the attention mechanism. You said that was important.
Hugely important. It might sound a bit technical, but honestly, it was crucial for the next big wave, the transformers.
Okay, so what does attention actually let the AI do?
Well, think of it as allowing the AI to focus its attention on the most relevant parts of the input data when it's generating something new.
So it understands context better.
Much better. Especially in long sequences like sentences or paragraphs, it helps track relationships between words, even if they're far apart.
Okay, that makes sense. So fast forward a bit, 2021, Dale.
Ah, yes. Daily and other text-to-image models, that felt like pure science fiction suddenly becoming real.
Right. You just type a description.
And boom,
right.
The AI generates an image matching it, often quite complex ones, too.
It was that combination of language understanding and visual creation that felt so new.
It really did. And the pace just kept picking up. 2022 rolls around.
And suddenly everyone could make AI art.
Pretty much.
Yeah.
High-quality image generation became much more accessible with tools like Stable Diffusion, Midjourney.
So democratized it in a way.
Exactly. Put these powerful creative tools into many more hands. And, of course, 2022 was also the year of ChatGPT.
Oh, boy. Yeah. That just exploded. Suddenly, conversational AI was the topic.
Captured everyone's attention. You couldn't escape it.
And it hasn't slowed down. Just last year, 2023, we got GPT-4 Claude.
Right. Even more powerful models, showing new capabilities, handling different types of data, multimodal stuff, and better reasoning.
Plus, the open source side really took off too, right? With Alama and others?
Hugely important. That open access is vital. It accelerates progress, lets more people build things, understand things, contribute back.
Okay, so that's the whirlwind tour of how we got here. Now let's dig into how generative AI is fundamentally different. It's not just like a faster version of old AI, is it?
No, that's a really key point. Our sources stress this.
What?
The core difference is the goal.
Okay.
Traditional AI, a lot of the time, is about optimizing for a correct answer from existing data. Is this email spam? Yes or no? What's the likely stock price? Predict a number?
Classification, prediction.
Exactly. Generative AI is different. Its goal is to create new, plausible data that resembles the data it was trained on.
Plausible being the key word.
Right. It uses different techniques like estimating the likelihood of something or minimizing reconstruction errors or that adversarial GAN process we talked about. It's aiming for coherence and novelty.
So traditional AI finds the right label. Generative AI invents something convincing.
That's a great way to put it, yeah. And this difference naturally flows into how we train them and how we evaluate them.
How so?
Well, traditional AI is often trained by directly comparing its output to a known ground truth answer. We know the right category, the right number.
Simple pass-fail, almost.
In a sense. With generative AI, there often isn't one single correct answer. If I ask for a picture of a cat astronaut, there are infinite possibilities.
Right. So how do you judge if it did a good job?
It's much more subjective. We look at things like, is the output diverse? Is it novel? Or just copying? Is it coherent? Does it make sense?
Human judgment comes into it more.
A lot more. We use things like reinforcement learning from human feedback, RLHF, where people rate different outputs. There are automated metrics too, but they often miss the nuance. Quality is harder to pin down objectively.
Okay, that makes sense. And this links to another difference you mentioned, autonomy.
Exactly. Because generative AI isn't just finding existing patterns but creating new combinations. It exhibits more autonomy. It can produce things that weren't explicitly in the training set.
That's where the cool, surprising results come from.
That's the upside. That's the innovation potential. But
it's always a but.
Well, it also means we have less direct, predictable control over the output. If it's inventing things, how do we make sure it invents the right things or safe things?
And understanding why it generated a specific output can be tricky, the whole black box problem.
It can be, yeah. The decision-making processes inside these huge models are incredibly complex, opaque even. That highlights the need for, guardrails, alignment techniques, careful control mechanisms.
Okay, so we've got the history, the key differences. What about the fundamental building blocks? Let's try and wrap our heads around the essentials without needing a PhD.
Sounds good. First up, parameters, weights, and biases.
Okay.
Think of these as the knobs and dials inside the model that get tuned during training. They store the patterns, learn from the data.
And there are lots of them.
Oh, yeah. Billions, even trillions in the really large models we see today.
Trillions, wow.
Yeah. And a big focus now is actually on parameter efficiency, getting more bang for your buck, better results with fewer, smarter parameters. It's not just about sheer size anymore.
Right, efficiency matters. Okay, next, tokens and vocabularies.
Right. So data needs to be broken down into pieces the AI can understand. These pieces are called tokens.
Like words.
Could be words, yeah. Or sometimes parts of words called subwords. Or even individual characters. It depends on the model and the task. The vocabulary is simply the complete list of all the unique tokens the model knows. And tokenization is the process of chopping up the input data, say a sentence, into these tokens.
How does it chop them up?
A common method is byte-pair encoding, BPE. It sort of learns the most efficient way to break words down based on frequency. There are also special tokens, like markers for the start or end of a sentence, that help the model understand structure.
So the choice of tokens matters.
Absolutely.
Yeah.
It impacts how well the model understands nuances, how efficiently it processes information, even what kind of things it can generate.
Got it. Okay, what about latent spaces and representation? This sounds a bit abstract.
It is a bit abstract, but it's a powerful idea. Imagine taking all the complex data the AI learned, all those images, all that text, and creating a compressed, sort of abstract map of it.
A summary map.
Kind of. A lower dimensional space where the essential features and relationships are captured. There's this idea called the manifold hypothesis, which basically suggests that even really complex high-dimensional data often lies on or near a simpler, lower dimensional shape or manifold. The AI tries to find that simpler structure.
And the latent variables.
Those are like the coordinates within this compressed map. Ideally, different coordinates control different meaningful attributes of the data. Like maybe one variable controls smiling in a face generator, another controls hair color.
So you can tweak these variables to change the output?
Exactly. That's representation learning. The AI learns to create this useful map. And if you get good disentanglement, where the variables control distinct concepts, you can manipulate the output in very controlled ways. It's key for generation.
That does sound powerful. Okay, last building block. Prompting and conditioning. This is how we interact with it, right?
Pretty much, yeah. This is the user interface,
Yeah.
essentially. A prompt is the input we give the model to get it started, the text description, the starting image, whatever. Conditioning is the broader idea of giving the model extra information to guide or influence what it generates. The prompt is one form of conditioning.
And prompt engineering is figuring out the best prompts.
Exactly. It's become a real skill crafting prompts that get the AI to produce exactly what you want. But there are other control methods too.
Like what?
Things like classifier-free guidance, which is used a lot in image models to strengthen the adherence to the text prompt, or control nets, which let you specify things like pose or outlines.
So more direct control.
Yeah. Even techniques like chain of thought prompting, where you ask the model to explain its reasoning steps first, help guide the generation towards more logical outcomes.
It's all about finding that balance, then, between control and letting the AI do its thing.
That's the constant tension, yes.
Yeah.
Balancing control and autonomy.
Okay, so these systems generate novel stuff. But is it really creative? That feels like a big, maybe philosophical question.
It absolutely is, and you need both technical and philosophical perspectives to really tackle it. It even links into theories of human cognition.
How so?
Well, technically, the AI is recombining patterns from its training data in statistically likely ways. Is that the same as human inspiration or insight? Probably not.
There's often that trade-off you hear about, right? Novelty versus quality.
Yes, exactly. Models often have a parameter, usually called temperature, that controls the randomness of the output.
Higher temperature means.
More randomness, potentially more surprising or novel outputs, but also potentially more incoherent or nonsensical results. Lower temperature is more focused, more predictable, often higher quality, but less adventurous.
So you can dial the creativity up or down, but risk getting garbage.
That's a decent way to think about it. And there are definitely limitations to current machine creativity.
Like what's missing?
The big one is probably a lack of true conceptual understanding. These models are pattern-matching wizards, but they don't understand the world in the way we do.
No common sense.
Not really. They struggle with causal reasoning why things happen, abstract concepts, metaphorical thinking, truly transferring knowledge from one domain to a completely different one. That's still very much a human strength.
So it can generate a poem about love, but it doesn't feel love.
Precisely. It's manipulating symbols based on patterns it learned without the underlying grounding in experience or deep understanding. Its creativity is still very much bound by its training data.
A crucial distinction. Okay, let's shift gears to the core tech. How do these things actually work? Keep it listener-friendly. Neural networks first. The basics.
Okay, the very basics. A neural network is made of interconnected nodes, or neurons. Think of them as tiny processing units.
Okay.
Each neuron gets inputs from others, multiplies those inputs by values called weights, adds another value called a bias, and then runs the result through an activation function.
An activation function.
Yeah, it's a simple mathematical function, like ReLU is a common one. It decides whether the neuron fires and passes on a signal. It helps the network learn nonlinear patterns, which is key for complex data.
And these neurons are in layers.
Right. An input layer takes the raw data, one or more hidden layers do the complex processing and learning, and an output layer gives the final result.
So simple units working together in layers, learn complex stuff.
That's the core idea. Now, for generative AI, there are specific types of these deep learning architectures that are important.
We mentioned GANs already.
We did. The generator versus discriminator. Architectures like StyleGAN really pushed image quality in GANs, though they can be tricky to train well. Things like mode collapse or instability.
Mode collapse.
Yeah, where the generator gets stuck producing only a few kinds of outputs instead of the full variety.
Okay. What else? VAEs.
Variational autoencoders. These work differently. They learn to compress the input data into that lower dimensional latent space we talked about.
Right, the map.
And then reconstruct the original data from that compressed representation. But they do it probabilistically, adding constraints that make the latent space smooth and good for sampling new data points from.
So compress, then reconstruct. But in a smart way that lets you generate new things.
Basically, yes. Then you have autoregressive models.
They sound like they work step by step.
They do. They generate sequences like text or audio waveforms one element at a time, predicting the next element based on all the previous ones.
Like finishing a sentence.
Exactly. They were important early on, especially for text, but transformers have largely taken over for many tasks now.
Which brings us back to transformers and attention. You said they were revolutionary in 2017. What was the big deal?
The self-attention mechanism. That was the game changer.
Okay.
Before transformers, models like RNNs process sequences step by step, sequentially. This made it hard to capture long-range dependencies, how a word early in a paragraph affects a word much later. And it was slow to train because you couldn't parallelize it easily.
Right.
Self-attention lets every element in the sequence look at every other element simultaneously, weighing how relevant each one is. It does this in parallel.
So it sees the whole context at once.
In effect, yes. Multi-head attention just means doing this multiple times in parallel, looking for different kinds of relationships. This solved the long-range dependency problem and allowed for massive parallelization during training.
Huge advantages.
Absolutely. And this led to the popular encoder-decoder architecture. The encoder reads the input sequence using self-attention, creating a rich representation. The decoder then uses that representation, also using attention, to generate the output sequence, often one step at a time, autoregressively.
And there are variations.
Yeah, you have encoder-only models like BERT, great for understanding input text. You have decoder-only models like the GPT series, designed for generating text. And full encoder-decoder models like T5, good for sequence-to-sequence tasks like translation.
And just making these transformers bigger led to new abilities.
It did. The sheer scale billions, now trillions of parameters, led to surprising emergent capabilities in models like GPT-3. Things they weren't explicitly trained for but could suddenly do. Though now there's also a lot of work on making attention more efficient for even larger models.
Okay, transformers are key. But you also mentioned diffusion models being really important now, especially for images.
Yes, they've become dominant for high-fidelity generation in many areas. They use a totally different process.
How does it work? Not the generator-discriminator thing.
No. It's a two-stage process. First, you have the forward process, where you gradually add random noise to your training data over many, many steps until it becomes pure, unrecognizable static.
Okay, destroy the data.
Sort of. But the key is the reverse process. The model learns to undo that noising process. It learns to take the pure noise and gradually, step by step, remove the noise to reconstruct a clean data sample.
Wow, okay. Learn to denoise perfectly.
Essentially, yes. It
Right.
learns the path from noise back to data. And crucially, we can guide this reverse denoising process.
Ah, the conditional part.
Exactly. Conditional diffusion models let us feed in information like a text prompt, and the model reverses the noise in a way that matches the condition. That's how text-to-image models like Stable Diffusion or DALL-E 2 work.
You can condition on other things too?
Oh yeah. Images, audio signals, layout maps, lots of possibilities. And techniques like classifier-free guidance help strengthen that conditioning.
And latent diffusion, like stable diffusion.
That's an efficiency trick. Instead of adding and removing noise from the huge high-resolution image directly, they first compress the image into that smaller latent space.
The map again?
Do the diffusion, noising and denoising process there, which is much faster, and then decode the result back into a full image. Huge efficiency gain.
Clever. And they're faster now. I heard early ones took ages.
They did. Early models like DDPM needed thousands of steps. But newer sampling techniques mean we can often get great results in just, say, 20 to 50 steps now. Much more practical.
Okay, so we have these incredibly powerful architectures. How do we actually train them? What are the main learning methods?
Well, the classic one is supervised learning.
Yeah.
You need paired data and input and the correct output, like English sentences paired with French translations.
Give it the answer.
Right. It's used a lot for specific tasks and for fine-tuning models. But the big limitation is needing all that labeled data, which is expensive and time-consuming to create.
Okay, so what else?
Self-supervised learning has been transformative. This is where the model learns from massive amounts of unlabeled data.
How, if there are no answers?
It creates its own learning tasks from the data itself.
Sure.
For example, take a sentence, mask out a word, and train the model to predict the missing word, like in BERT. Or train it to predict the next word in a sequence, like in GPT.
Ah, so the supervision signal comes from the data.
Exactly. This lets us leverage the vast amounts of text or other data available online to train incredibly powerful foundation models without needing humans to label everything first.
That sounds like a massive unlock.
It was. Then there's contrastive learning.
Kind of.
Learning by comparing things. The model is shown pairs of things that are similar, like a picture of a dog and the text photo of a dog, and pairs that are dissimilar, like the dog picture and the text photo of a cat. It learns to pull similar things together in its representation space and push dissimilar things apart.
Useful for connecting different types of data.
Hugely. Models like CLIP, which links images and text, rely heavily on contrastive learning. It's vital for multimodal generation.
Okay. And we mentioned RLHF before, reinforcement learning from human feedback.
Right. This comes in usually after a model has been pre-trained with self-supervised learning. It's about fine-tuning the model to better align with what humans actually want or prefer.
How does that work? People voting?
Kinda. Typically, humans are shown multiple outputs from the model for the same prompt and rank them from best to worst. This preference data is used to train a separate reward model that learns to predict human preferences. Then reinforcement learning algorithms, like PPO, are used to update the main generative model to maximize the score from this reward model, basically teaching it to generate outputs that humans are likely to rate highly.
So steering it towards helpfulness and harmlessness, like with ChatGPT.
That's the goal, yes.
Yeah.
Aligning it with human values. There are also related ideas like constitutional AI.
Constitutional, like a rule book.
Sort of. Instead of direct human feedback on every output, the AI is guided by a set of principles, or a constitution, during its training, aiming to make it behave according to those principles without constant human oversight. Anthropic uses this a lot.
Interesting. And lastly, few-shot and zero-shot learning.
Yeah, this is a capability that emerges from large-scale pre-training. Zero-shot means the model can perform a task it was never explicitly trained for just by being given an instruction or prompt.
Like ask it to summarize text, even if it wasn't trained only on summarization.
Exactly. Few-shot means it can learn a new task from just a handful of examples given in the prompt. It leverages its broad pre-trained knowledge. It's incredibly powerful.
It's amazing how many ways there are to teach these machines. Okay, the really exciting part. What can generative AI actually do today? Give us some examples.
The list is getting long. Image generation is huge, obviously. We mentioned Stable Diffusion, Midjourney, Dall-E.
Right.
Open source models like Stable Diffusion have been massive, plus GANs like StyleGAN for super high-res faces, and even generating vector graphics now.
And editing images too, right?
Definitely. Image editing and manipulation using natural language prompts is getting really good. Tools like Adobe Firefly integrate this, or in-painting with Stable Diffusion, where you can just describe the change you want. Style transfer is still around too.
Wild. What about sound, audio, music?
Big progress there too. Speech synthesis, text-to-speech, is incredibly realistic now. Models like WaveNet, Talkatron, and newer ones. Voice cloning is also possible, though ethically tricky. For music, AI systems can compose melodies, harmonies, entire tracks in different genres, generate background music, sound effects.
An AI composer and sound designer.
The potential's there. Video generation's coming along too, though it's maybe a step behind images.
Harder to keep things consistent over time.
Exactly.
Right.
Temporal consistency is a big challenge. But we're seeing text-to-video models emerge, image-to-video for animating stills, motion synthesis. It's moving fast.
And putting it all together, multimodal.
Yes, that's a huge frontier. Vision language models that understand both images and text deeply. Audio-visual systems, cross-modal translation generating text from an image or vice versa. Even embodied AI, where models control agents in simulated worlds based on multimodal inputs. And multimodal reasoning, answering questions that require understanding information from different sources.
Okay, the capabilities are stunning. But we have to talk about the other side. The ethical maze. This stuff isn't simple.
Not at all. It's probably the most critical area to get right. Bias and fairness are huge issues.
Where does the bias come from?
Mostly from the training data. If the data reflects historical biases, societal inequalities, stereotypes, the AI will learn them and potentially amplify them.
So garbage in, garbage out. Or worse.
Often worse due to amplification effects.
Yeah.
There are many types of bias representation bias, certain groups being underrepresented. Measurement bias, algorithmic bias introduced by the model itself, interaction bias from user feedback. It's complex.
How do we fight it?
It requires a multi-pronged approach. Carefully curating and augmenting training data, reweighting samples using adversarial techniques to train against bias, fine-tuning with specific fairness goals, careful prompt design, building checks at the system level.
It sounds like a constant effort.
It has to be. And defining fairness itself is hard. Does it mean equal outcomes? Equal opportunity? Depends on the context, and there are often trade-offs. Ensuring diverse representation and accessibility for everyone is paramount.
Okay, bias is one thing. What about privacy?
Another major concern. First, the data used to train these massive models. Was there proper consent? Is the data truly anonymized? It's hard to guarantee, especially with web scrape data.
Can models leak private info they were trained on?
Yes, that's called memorization. Models can sometimes regurgitate specific training examples, including personal information, if prompted correctly. There are techniques to mitigate this, like differential privacy or federated learning, but they have limitations.
And our data, when we use the AI.
How user prompts and interactions are handled is crucial. Transparency and user control are key. And then there's the use of synthetic data, AI-generated data, which might help sometimes but raises its own questions. The right to be forgotten is also really hard to implement with these huge, complex models.
Okay, copyright. If AI generates an image or music, who owns it?
The million-dollar question. Legal systems are scrambling to catch up. Current U.S. guidance suggests purely AI-generated works without significant human authorship might not be copyrightable. But where's the line?
What about the data used for training? Did the AI creators have the rights to use all those images, texts, code snippets?
That's the basis of several major lawsuits right now. Is training on copyrighted data fair use or infringement? The outcomes will be huge. We also need clear attribution models and licensing frameworks for AI-assisted or generated content.
Messy. And then there's misinformation, deepfakes.
Yeah, synthetic media. Generative AI makes it easier than ever to create convincing fake images, videos, audio deepfakes, and text models can generate plausible-sounding misinformation or propaganda at scale. Models can also just hallucinate, make stuff up confidently.
Can we detect this fake stuff?
There are detection technologies, but it's an arms race. As generators get better, detectors need to improve. Watermarking AI content or using content authentication systems might help, but they're not foolproof. Media literacy becomes even more critical for everyone.
So laws and regulations are needed. Governance.
Definitely. We're seeing efforts emerge, like the EU AI Act, which takes a risk-based approach. There are international initiatives, industry self-regulation attempts, standards being developed. But it's challenging to regulate such a fast-moving global technology effectively. Enforcement is tricky, too.
So it really comes down to responsible development.
Absolutely. Building ethics in from the start, ethics by design. Conducting thorough impact assessments. Engaging with stakeholders. Being transparent. Documenting processes. Continuously evaluating models after deployment. Adhering to ethical guidelines and codes of conduct. It needs to be baked into the entire life cycle.
It feels like we're just at the beginning of figuring all this out, even as the tech races ahead.
That's exactly right. The pace of capability development is often outstripping our ability to fully understand and manage the societal and ethical implications.
Okay. To wrap this all up, what's the single most important thing you think our listeners should take away from this deep dive today?
I think the key takeaway is that generative AI is a truly powerful, transformative technology. It's shifting AI from analysis to creation, opening up immense potential, creative, scientific, economic, but it comes with significant responsibility, understanding its foundations, its capabilities, and especially its ethical challenges. Bias, privacy, truth, control is absolutely crucial for everyone, not just developers, as we navigate how to use it wisely.
Absolutely. Well, hopefully this discussion has given you, our listener, a solid grounding in this complex and fascinating field, from its roots to where we are now and the big questions we face.
Yeah, I hope it was a useful shortcut through a lot of information.
So here's a final thought to leave you with. Considering generative AI's power to create entirely new realities, what do you believe is the defining responsibility for those of us developing, deploying, and even just using these systems in the years ahead?
That's a big one to ponder.
It is. Something to think about and maybe explore further based on what sparked your interest today.